Welcome to The Explainer. Today we're going to tackle a concept that's honestly everywhere. It's called sets, and believe it or not, you use this idea all day, every day. It's also the foundation for some really big stuff, like computer programming and even formal logic. So let's just start with a really big question, right? How in the world do we make sense of everything around us? I mean, every single day, you're hit with tons of information, different faces, all kinds of food. How do we even begin to sort it all out and not just live in total chaos?
Well, the answer is actually pretty simple. We group things. It's what our brains do naturally. We're constantly making little collections to understand the world. Like grouping the different types of teeth, or all the books in a library, or even just your favorite songs on a playlist. It's all about creating order. And this is where math comes in. It takes this basic, powerful idea of grouping things and gives it a formal name, a set. Now, there are a couple of key rules here. A set has to be well-defined, which just means you have to be able to say for sure if something is in the set or not. And the objects have to be distinct, which is a fancy way of saying no repeats. So the big takeaway here is that sets aren't just some weird, abstract math thing. Nope, they're a tool you already use every single day to organize your world. All math does is give us a super clear and precise language to talk about it. All right, so let's get into the nitty-gritty. We're going to learn the two main ways that mathematicians actually write down and describe these sets. You can think of it like learning the grammar for this new language. So you've got two main options, and they're basically just two different ways to say the exact same thing. The first one is called roster form. It's super simple. You just list out every single thing in the set. The second one, set builder form, is a little more elegant. Instead of listing everything, you just write a rule that describes what's in the set. Okay, let's make this real with an example we all know. We're going to describe the set of vowels in the English alphabet.
So using that first method, roster form, this is as easy as it gets. You literally just list the elements, A, E, I, O, U, and stick them inside these curly brackets. That's it. Done.
Now, what about set builder form? This way you state the rule, or the property, that everything in the set has to follow. You'd read this out loud as V is the set of all elements X, such that X is a vowel in the English alphabet. See? It's basically a rule that tells you how to build the list yourself.
And this table here, this really drives home why you'd want to use both forms. I mean, for the vowels, either way is fine, right? But check out set A. The list is pretty short, but the rule, X is an integer, that's what that Z means, from -2 to 2, is so much cleaner. And then look at set C. The rule, x equals n squared plus 1, where n is a natural number up to 4. Wow! That rule actually shows you the pattern behind the numbers. You might totally miss that beautiful logic if you only saw the list.
Okay, so we know how to write sets. Awesome. But now for the fun part. We're going to learn how to actually do stuff with them, how to combine them, compare them, all that good stuff. This is where we really start putting sets to work to solve problems. First up is something called the union. You'll see it written with this little U symbol. And don't worry, the name sounds way more complicated than it is. A union is just combining everything from both sets into one big superset. That's all.
And if you look at it with a Venn diagram, it's super obvious. The union is literally everything you see shaded in, the whole area of both circles. If something is in set A or in set B or even in both, it's in the union. It's the whole shebang.
So let's walk through how to actually find a union step by step. First, you just take all the elements from set A and all the elements from set B and kind of throw them all together in one big list. But then, and this is the most important part, you got to remember that rule about sets having no repeats. So you look for any duplicates. In this case, the number 5 is in both sets, so we just get rid of one of them. What's left is your union. Easy peasy. Okay, next up, intersection. This one looks like an upside-down U. And if you think of union as being all-inclusive, like a big party, then intersection is the total opposite. It's super exclusive. We only care about the elements that are in both sets at the same time. And again, the Venn diagram makes this crystal clear. The intersection is not the whole circle for A or B. It's just that little sliver in the middle where they overlap. It's only the stuff they share, period. So let's actually solve one. We've got set A and set B. We're basically just playing a matching game. We look at both lists and hunt for the numbers that appear in both. Is 5 in both? Nope. 6? Nah. But wait, 7 and 8? Yep, they're in both. So we pull those two out, and that's it. That's our intersection, the set containing just 7 and 8. All right, last one for now, the difference.
The easiest way to think about this one is just like subtraction with numbers. If we want to find A minus B, we start with everything that's in set A, and then we take away anything that's also in set B. What you're left with is the stuff that's only in A and nowhere else.
Okay, time to put it all together. Let's take what we've learned and actually solve a problem from start to finish. This is where the rubber meets the road.
So here's the challenge. We've got set A and set B. The question is, what is A minus B? So just remember the rule. We're going to start with everything in A, and then we're going to subtract, or remove, anything that also shows up in B.
Let's just walk through the steps, nice and easy. Step 1, we start with set A. That's the numbers 1, 2, 3, 4, and 5. Step 2, we look for the overlap. Which numbers from A are also in B? It's 4 and 5. Step 3, we take those overlapping numbers and remove them from A. So we cross out the 4, we cross out the 5. And what's left? Just 1, 2, and 3. And that's our answer.
And there you have it. That's how you use all these ideas, this language of sets, to solve problems step by step. But that leaves us with one last little brain teaser to think about. We just figured out what A minus B is, but what about B minus A? Would you get the same answer? In other words, when you're finding the difference between sets, does the order actually matter? I'll leave that one for you to figure out.